Right, good morning, everybody. We're going to get started here in just a minute. I am pleased to introduce Professor Mark Benjamin from the University of Washington, Civil and Environmental Engineering. Professor Benjamin received his undergraduate education at Carnegie Mellon University in chemical engineering, and then he went to grad school at Stanford, where he received a master's degree in chemical engineering and a PhD in environmental engineering in 1978, working with Jim Leckie. He then went on to a faculty position at the University of Washington in Seattle, where he's been since as a distinguished career spanning 38 years. Professor Benjamin is an expert in physical chemical treatment processes, with particular emphasis on the removal of natural organic matter, metals, and other contaminants from potable water sources using adsorption and membrane processes. He's also a prolific writer. He's the author of a widely adopted water chemistry textbook, and more recently of a textbook, a graduate-level physical chemical processes textbook, which he co-authored with Des Lawler from the University of Texas. He's garnered a number of awards during his career, including the AWSP Distinguished Lecturer Award in 2009, and a number of chaired professorships at the University of Washington, and we're pleased to have him speak here today. Thank you, Mark.
Thanks, Santiago. I hope you feel the same way at the end. It's a pleasure to be here. I was just saying I have a daughter who teaches at St. Olaf, so I come to St. Paul fairly frequently, but this is only my second opportunity to visit here, and I'm looking forward to talking to you now and then meeting several of you afterwards. I'm going to tell you today about a career-long pursuit that, as Santiago said, I started out studying adsorption. That was my doctoral thesis. It was adsorption of metals, but I continued an interest in adsorption, moved on, looked at adsorption of organic materials, and then actually a student dragged me into the membrane research area about 25 years ago, and it was the combination of adsorption and membranes that has fascinated me for the last 25 years, and that's what I'll be talking about today. My understanding is that this is a departmental seminar, meaning that we have people who are in environmental and probably even some specialists in areas fairly closely related to what I'm talking about, and others who probably have very little background in this. So I'm going to try and thread that needle and talk to all of you in a way that makes sense. Most of the talk is going to be phenomenological. It's not detailed chemistry. There's a little bit of chemical interpretation here and there. And I'll be happy to, of course, answer questions in more detail later if anybody is interested. But really, I'm going to try and compress 20 years into the next 50 minutes and tell you about the thought processes that we went through and the exciting successes we had and the less exciting disappointments we had, of which there have been many. So let me just jump in. The pro forma slide about the fact that membranes have been used increasingly over the last 25 years. The upper slide, the y-axis is not labeled, but it's millions of dollars invested in membrane technology, membrane plants worldwide since 2002. I believe the data actually go through 2012, and the subsequent 4 years are for projections. But you can see that from 2002, when there was about $750 million being invested, and the projection for this year is over $2 billion, that membranes have, in fact, been a growth area within the field. And back in the 1990s, when I started this work, I used to try and convince people that membranes were the wave of the future, and now I think it's fair to say they're the wave of the present. This figure on the right just shows the distribution of applications, mostly in drinking water, although wastewater applications are certainly increasing these days. On the left is the kind of membrane that is most commonly used in drinking water treatment. This is epoxy, and these are fibers, long fibers that are about a couple of millimeters in diameter with holes through the middle. They're basically very tiny straws. And the way this works is that water is pumped in from this end under pressure, and as it moves through these straws that, of course, go behind the screen, the water migrates or diffuses through the pores in the membrane, and it goes to the outside of the fibers where it's collected. And the reason that these fibers are so small is that the processing rate per fiber is extremely small also. A typical flux, which is the way the flow rates are characterized in these systems, might be 60 liters per square meter of surface area per hour, and that corresponds to 1 millimeter of velocity, 1 millimeter per minute of velocity. Okay? So you think about a millimeter, and you think taking a minute to go that far. This water is not flowing like through a pipe, right? It is migrating extremely slowly, and that's going to be important later. And of course, because very little water comes out of each fiber per minute or per hour, you need a lot of fibers in order to process enough to treat water for a city. Okay, I'm going to be talking about fouling of membranes. I think it's not a great exaggeration to say that of all the research in membrane technology these days, and there is a ton of it, the vast majority is addressing one question, which is how to reduce membrane fouling. Membrane fouling is caused by the fact that membranes work. You take water that has contaminants in it, you push it through the membranes, and the whole idea is to reject the contaminants, to keep the contaminants on the inside while the water goes through the fiber. But that means that those contaminants accumulate right at the interface between the water and, in this case, in the pictures I showed, the interior of those fibers. And those contaminants build up quickly and resist flow of additional water. So the very fact that the membranes work so well and remove contaminants so well causes them to work less well as time goes on because of the accumulation of contaminants. The natural organic matter is not a human-induced contaminant. It's the residual from the decay of plants in the watershed. And it's in every water, and especially in surface waters, lakes and rivers. It's what makes water look a bit yellowish. This is water that has a fair amount of natural organic matter in it. And the natural organic matter consists of a bunch of organic kinds of compounds that, as I say, cannot be easily characterized because they're just taking trees and chopping up little pieces of them, molecular pieces, and they all have different sizes and different characteristics, although they certainly have some common characteristics among them. But there's a lot of different kinds of molecules. And so membranes are already widely used in water treatment technology, but their efficiency and their wider adoption is limited by their tendency to foul. Now, this is the only molecule I think I'm going to show you in the next hour, and it's just some guy's idea of what a natural organic molecule looks like, and we don't have to worry about it. But it causes problems in a number of areas. One is that when we disinfect water with chlorine, the chlorine attacks these portions of these molecules and forms disinfection byproducts like chloroform that are carcinogenic. And so it's good to get this stuff out of the water before you disinfect it to minimize the production of the disinfection byproducts, which are highly regulated by EPA, but are present in every water that is chlorinated. These things can also interfere with other kinds of water treatment processes like adsorption onto activated carbon. I'm not going to talk about that today. What I'm going to be talking about mostly is that they cause membrane fouling, as I just described. Now, this is what membrane fouling looks like. This is a small disc that we use in a lot of our experiments. It's just about this big, and we pass water through it. And as we pass water through it, the disc turns sort of yellowish. And that's the natural organic matter that has been rejected from the feed and is collecting on the surface. Right? Now, what's the consequence of that? Well, this shows, and we don't have to worry about the numbers or even the label, but this is the resistance caused by the accumulated organic matter as a function of the amount of water processed. And I'll be using this parameter a lot in the slides that I show. We label it V sub SP, the specific volume treated. It's the liters of water treated per square meter of membrane surface. So it's basically how much water has passed through each little square of membrane. And left to right is just the progression of a membrane run. And up here we have pictures of what the membrane looks like, scanning electron micrographs of the surface of the membrane at various times. These numbers are for the resistance, and it's calculated in a conventional way. I say we don't have to worry about the numbers, other than to let you know that the resistance of a clean membrane, a brand new membrane, is down here around 5 by 10 to the 11th. Right? Now, this is just the increase in membrane resistance due to the collection of organic matter on the surface. And what we see is that, oh, and I forgot to mention that for a typical kind of flow rate, somewhere around 60 or 70 units on this x-axis corresponds to 1 hour of treatment. Okay, so this is about 6 or 7 hours of water passage through the membrane. And you can see that within 1 hour, the resistance caused by the accumulation of organic materials on that surface is about equal to the resistance of the bare membrane itself. So the total resistance has doubled within an hour. And if you go to 5 or 6 hours, the resistance caused by this accumulation of material far exceeds the resistance of the membrane. Right? And you can see the pores in the membrane here. This happens to be a membrane with pores that are about 25 nanometers average opening. And you can see that over time, the pores narrow, and then eventually it looks like they're completely covered by this coating. But in fact, this coating is somewhat porous. We can still push water through here, but it's a lot harder to do it than when the membrane is clean. Right? Now, this is an edge-on view of the same system. This is the organic matter that has accumulated on the membrane. This down here is not the membrane. This is just a spongy material that provides the backing for the membrane. The membrane itself is a very thin line here that's almost invisible to see. The membrane is less than a micron thick and, I say, is just on top of a spongy material where the sponge is providing the structural support. So what we can see here is that not only does this natural organic matter accumulate, but it actually changes form. And this is going to be an important point that I'll come back to a couple of times. People think of membranes as removing individual particles. The early uses of membranes were for removing particles from water, and the intention wasn't to remove dissolved material like organic material, but they do so anyway. Now, the thing is that in the water, I showed you that yellowish water, there are not tiny particles of stuff that looks like this. The molecules are completely dissolved. But when they hit the membrane, they actually undergo a phase transition. I think this is not fully appreciated in the field. The natural organic matter fouling is not caused by the accumulation of molecules here and there, but rather by the condensation of molecules into a new phase at the surface. Now, two things worth pointing out about this figure. One is that this membrane would never really be used for this long without being cleaned. If we went to this stage, it would be way too hard to push water through it. This is an exaggeration. The other thing is that this accumulation, although it looks, in this image like, wow, there's a lot of stuff there, the fact is that only less than 3% of the organic matter in the feed was removed. We measured how much organic was in the feed and how much was in the permeate, and over 97% of the organic matter passed right through. So we have the worst of all worlds here. We'd like to get natural organic matter out so that we don't form disinfection byproducts, but we only get 3% out, and yet that 3% causes the membranes to perform very poorly. Okay? So what do we want to do? Oh, what do we do about that? The truth is, the way membranes are operated is that the pressure, this is the pressure required to push water through the membrane, and this is time, and this is a made-up diagram. There's no data here. It looks like they're data points, but it's just hypothetical. What happens is that as we start the process, there's some pressure required to push the water through the bare membrane. Then the pressure builds up over time because of the accumulation of organics. And then at some point, we clean the membrane and try and get it back to its initial state. And we usually do a pretty good job of cleaning it, but we never recover 100% of its capacity. And so it gets a little bit worse after each cycle. And after many cycles, we might have to do a more aggressive cleaning using chemicals in addition to just, these cleanings are done by hydraulic shear, just by scouring and backwashing. Okay? All right. So what is done to reduce fouling? Mostly what's done is, the screen partially cuts this off. It says conventional membrane treatment, is to add a coagulant to the water to collect the natural organic matter prior to putting the water onto the membrane. There are coagulants, alum and ferric chloride are the most common, that are good at collecting a substantial amount of organic matter and thereby removing that organic matter from the solution before the solution is passed through the membrane. And that's done in two ways. This little cartoon, the circles, the green circles, are meant to be aluminum hydroxide or iron hydroxide particles, which actually do the collection, and little squiggles are the natural organic matter molecules. And if we have a low concentration of organic matter in the water, then we can dose a small amount of these coagulants into the water, and we can apply this water directly to a membrane, and the membrane removes the particles as well as the organic matter that's attached to the particles, and some of the organic matter does not attach to the particles, and that still gets to the membrane and migrates through. But a lot of the organic matter is stuck on these particles, and the particles prevent the organic matter from actually touching the membrane. So that helps. Okay? But still, you have to backwash the membrane fairly frequently because these particles and the organic matter accumulates. Now, if there's a high concentration of organic matter in the water, you have to add a high dose of the coagulant, but then the concentration of particles here is too high, and if we applied this water directly to the membrane, all those particles would plug up the membrane. And so in that case, we have to add a settling step or some other filtration step that gets most of the particles out, and then what we end up passing on to the membrane is just the organic matter that has not attached to the particles and a few of the particles that didn't get removed, and we get this situation. In both these cases, we get fouling. In this case, because of the organic matter that was not removed, and in this case, both because of the organic matter that was not removed and because those coagulants, as I say, tend to foul the membrane themselves. So what did we do? Again, I'm jumping ahead of myself. I want to just say that powdered activated carbon, ferric chloride, and alum have all been tested as ways to remove this organic matter. And this is, an unfair selection. It's not, the plus means they help, the minus means they made things worse, plus or minus means they didn't have much effect. It's not true that they only help half the time, but there are plenty of times when those added particles cause more fouling than the organic matter that they're removing. And so it's not a guaranteed success just to use coagulant. So what are we going to do? Well, there's a summary here of what I've just showed, that direct microfiltration or ultrafiltration, those are the names for the membranes that we use. They remove very little natural organic matter. They are rapidly fouled. Some irreversible fouling occurs, and they require frequent backwashing. If we use conventional pretreatment, we can coagulate some of the NOM with alum or ferric chloride, remove some of the NOM, often reduces fouling. Frequent backwashing is still required, and irreversible fouling is still a problem, and the performance is somewhat inconsistent depending on the water quality. So our goal was to remove at least as much natural organic matter as could be removed here, and dramatically reduce fouling and backwashing requirements and improve the performance reliability. And I will show you how we tried to do that. Now, these are just small versions of what I showed you earlier. They're exactly the same. And what we decided to do was find something that we could put on the membrane first, not mix in with the water, but rather deposit on the membrane, and then just add the water and pass the water through here and hopefully collect the NOM on the particles before the water got to the membrane. Now, you could well say, well, wait a minute here. You just told me that those particles are going to plug the membrane. So we did something to make them non-plugging or non-fouling, and I'll tell you about that in a minute. First of all, let me show you how we made them. We took alum, the conventional coagulant that's used more often than any other, so it's a conventional additive. We added sodium hydroxide to neutralize it to pH 7, and that causes flocks to precipitate. Now, this is conventional treatment. If we did this in the water to be treated, these flocks would be the things that collect the organic matter. Okay? And they are, in fact, flocculent. They look like snowflakes. Okay? They're big, fluffy particles. We then took that material and we precipitated the alum not in the raw water but in clean water, deionized water. We heated it in a closed container. We did that for more than 8 hours, and we saw that the particles were transformed, and they were transformed into a powder that made the water look milky white. Right? So now I couldn't show it in the same way here, because if I made it at this concentration, the particles would be almost invisible. They're tiny particles. But if you take these particles and you rub them between your fingers, it's sort of like a micro sand. It's not fluffy particles. What's happened here is that the heat has partially dehydrated those particles. It's taken the aluminum hydroxide that also incorporates lots of water into it, and it has squeezed the water out while keeping the aluminum hydroxide there. Now, we tried this in open containers also, and it didn't work. For reasons I can tell you later. But anyway, that's why we do it in a closed container. Here are a few of the characteristics of these particles. They have a fairly wide particle size range, but from a couple microns up to a few tens of microns. We think the average is around 7.5 microns. Point of zero charge at 7.7. They have a surface area of a little over 100 square meters per gram, and they are about 28% aluminum, which corresponds roughly to a chemical formula that says for every aluminum hydroxide molecule that's formed, there is 1 molecule of water in the solid. And that's as opposed to this stuff where the aluminum hydroxide has a lot of water incorporated into it. So we squeezed a lot of water out of the particles. I'm going to tell you about treatment that we conducted with 2 waters. We also did some tests with synthetic waters, which I'm not going to talk about today, but again, I'll be happy to review that if you have questions. The waters we used, one had a relatively low organic concentration. This is deionized water, but it looks almost as good as that. It's very clear, clean water that's right near the university, right adjacent to the university. And then some water that is from a lake called Lake Pleasant, which is not. But it has a high concentration of organics, 15 to 20 milligrams per liter. We used this both because it's more typical and because for some of our processes we need a lot of water, and we have direct access to this a line going straight out to the lake, and so we can pump it right into our lab. Whereas this stuff we have to go out and collect, and we can't collect huge amounts, so that's why we use both. Okay, first of all, the question was, when we heat the particles, do they retain their ability to collect organic matter? And this is showing a comparison of the particles we make that I will call HAPs. That stands for heated aluminum oxide particles. And this compares the amount of dissolved organic carbon removed by the particles as a function of the amount of the particle that we add. And we used 3 conventional particles: aluminum hydroxide, which comes from alum, iron hydroxide, which comes from iron chloride, and powdered activated carbon. And then we compared that with heated aluminum oxide particles, looking at the removal of organic carbon as a function of the dose. And what we found was that although the particles were all comparable, and in fact powdered carbon was better than HAPs at high doses, this is the region where you want to live if you're going to be operating at a water treatment plant. This is a lot of stuff to add. But you want to be down in this range. And in this range, the heating actually enhanced the ability of the particles to collect organic matter, which was pure good luck. I mean, we didn't predict that at all. We were hoping it would be as good as these, but in fact, it's better at these ranges. Okay, so that was good news. Next, we took the particles here, and we did a test where rather than just adding them into a batch of the raw water, we operated the process as I described, which is to say we first took the HAPs and pumped them through. There is a membrane here, that's the blue line. The HAPs formed a coating on the membrane, and then we took water from Lake Union. Here, this is a very typical day in Seattle if you've ever visited. What's the laughter? Come on. This is Mount Rainier. We take water from here, we pump it through, and we collect it, and we see how well it performs. You know that, right? So, how did it perform?
It's 3/4 before I saw Mount Rainier.
Yeah, but the quarters go quickly. So, I told you before that we said that alum coats the membrane and causes fouling by itself. What's different about HAPs? Well, the difference is this amount of water. As I said, when we heat the alum flux, this N, which is a big number, I don't know how big, turns into 1. And so we get rid of a lot of the water, and instead of these things being what I think of as tiny water balloons, that when they hit the membrane and are compressed, they just sort of spread out and completely block the pores, we have something that's closer to micro sand, where we form a layer here of hard particles that maintain the spaces between them for water to pass through. Okay? So, we wanted to test that hypothesis, and just a quick result here. It's very simple. Oh, I need to explain this test. We just took, we put a layer of HAPs on our membrane, and then we took the downstream effluent line, and we put a needle valve on it, and we gradually closed it, and we pumped water through at a constant rate. So the tighter this needle valve was, the more back pressure there was, and the more those HAPs were being compressed. Right? We just were basically causing the higher and higher pressure to be applied to the feed in order to push it through the membrane. And when we did that, we had pressures on the red curve going here. The applied pressure went from almost 0. We went up to 2.5 atmospheres. So what? 35, 40 psi, 225 kPa. And as we applied more and more pressure, the layer was being pressurized, compressed, but the pressure required the difference in pressure, the difference between the pressure here and here, which is being measured with transducers, was constantly between 1.5 and 2 psi, no matter how much we compressed it. So that just showed that when we were pushing the HAPs together, the openings were staying at the same size. It was just as easy to push the water through when the particles were pressurized as when they were not pressurized. So in fact, that idea that those particles would maintain their open spaces, their pore spaces, under pressure was validated. Well, now on to the real results. This is a comparison of the two modes of treating water that I described earlier. First, we have a control test where I'm showing the pressure required, again, the pressure required to push water through the membrane as a function of the volume treated in a run. And these open circles here represent what happened when we just had the membrane there and nothing on the membrane. We just took the water and passed it through. And the pressure built up very quickly, as you can see. Then we did this test where we mixed HAPs now in with the raw water to collect some NOM. And then we put that material through the membrane, including the HAPs, and we passed the water through the membrane. The HAPs were trapped by the membrane, and we see that, well, it wasn't bad. It took about twice as long before the membrane got fouled. The rate of fouling was reduced because the natural organic matter was being removed. Then we took that same amount of HAPs, and rather than mixing it with the raw water, we put it on the membrane and just passed the raw water through, and we just about fell over when we saw this. This is what happened in that case. The rate at which the pressure built up in this system, even though we were using the same amount of particles as we used here, was the rate of pressure buildup was more than an order of reduced by more than an order of magnitude. So the fouling mitigation was enormously better using the same materials but just applying them in a different way. Okay, now I'm not even going to go through this other than to say we did this with 4 different kinds of membranes to convince ourselves that it wasn't a unique result for the membrane, that we weren't just lucky choosing a particular membrane. The HAPs work as you would expect before the water ever gets to the membrane, so it really doesn't matter what the membrane is, the HAPs remove the foulants. Okay. So, summary at this point, membrane fouling can be severe despite removal of only a small amount of natural organic matter. HAPs appear to be an effective adsorbent that is a collector for natural organic matter. HAPs layers are incompressible, and predeposition seems to protect most, if not all, membranes from fouling much more effectively than pre-adsorption, that is the conventional process of mixing the water with the adsorbent, or direct filtration, which just is essentially the same thing. Okay, next, I want to show you several slides that are, I think, visually compelling, just to look at what the NOM looks like when it gets collected on the HAPs. But there's also information there that I want to provide to you and tell you again about our thought process. This is a clean membrane. Those of you in front probably can see that there is in fact a layer of something there. That's the HAPs when they're freshly deposited. They're white, so you can barely see them against the membrane, but it's there. And this again shows the surface of the HAPs at various times during a run. And I put this slide from earlier up there to show you, remind you what the membrane looked like without HAPs. The membrane does yellow over time, but in this case you can see that it turns golden yellow and then brown and then deep brown. The HAPs just keep collecting this NOM on the surface, much more so than the bare membrane does. And then the really interesting thing is that when we took, this is the cartridge that the membrane is holding, this is the membrane, we opened up the cartridge and we just sort of squirted some of the HAPs off, but left some of them there. So this is the surface that we were looking at before, and this, you can't really see it again because it's white on white, but there are HAPs here that we can see that are below the surface, and they're still white. They didn't turn yellow. And then here's the membrane surface. So we took a little chip of this layer, and we tried to take a picture edge on, and we were using our cameras, so we didn't get a very good picture of our phones. But anyway, this is the surface, and there you can see it. It looks like all the NOM that's being removed is being removed right at the surface. And so then we did a chemical analysis. This, again, is a scanning electron micrograph of the HAPs layer at various depths. We did an analysis of the ratio of carbon to aluminum, carbon being from the organic matter. And you can see there's a ratio of, I believe this is in percentages, a percent ratio rather than the absolute numbers. But there's about 1 or 2% as much carbon as aluminum through here. But right at the surface, we have 23 atoms of carbon for every atom of aluminum. So obviously, that organic matter is really concentrated up there. And again, let me remind you about the tendency for organic matter to form a gel or to coagulate on the membrane surface. So our interpretation, our tentative interpretation, was this, that gel is still forming, but it's forming at the surface of the HAPs, that's the yellow stuff, rather than forming on this surface, and that's why the surface looks yellow and then brown, but that we can form a much thicker layer of gel here than here, because when even a relatively thin layer forms here, it blocks the water and we have to stop. Whereas here, the gel forms on the individual particles and there's still space between the particles for water to flow, so we can go for a longer time and we get more gel accumulated. And then we had what we thought was an epiphany. We thought, oh my God, this is better than we ever imagined. Because what it suggests is that all we really need is the thinnest possible layer of HAPs, because all the action's right at the top. And here's a little cartoon that shows that. The idea being that over time, the stuff that we're worried about is all accumulating at the surface, so we could in fact have a layer that was just this thick, use very little HAPs, and we'd accomplish the same goal. So our hypothesis was that NOM and foulant are removed in a thin layer of HAPs at the feed HAPs interface, and therefore NOM removal and fouling reduction should be insensitive to the thickness of the HAPs layer as long as a small minimum thickness is used. And so we did that experiment, and guess what? We were so wrong. We were so wrong, right? Here we have tests where we have a control with no HAPs, and then 3 different thicknesses of HAPs expressed here in grams of aluminum applied per square meter of membrane, 4.5, 9, and 18 grams of HAPs. And every time we added more HAPs, the performance improved, which is completely the opposite of what we expected. We thought when we made the layer thicker that the performance would be identical, right? So failure, right? And here, just to twist the knife, we looked at the NOM removal with no HAPs. 100% of the NOM comes through, so the normalized DOC, that's the DOC in the permeate compared to that in the feed, is around 1. When we had the HAPs layers, the NOM removal was good. It was about 60% at the beginning in all cases, but when we had a small amount of HAPs there, it started breaking through earlier. And the more HAPs we added, the more NOM was removed. So obviously, there is something going on at the surface. You saw the color just like we did. Right? There's something different happening there. There is some gel formation. But the absence of gel, or at least the absence of color in the interior of the layer, does not imply that there's no organic removal there. There is organic removal throughout the layer, and to a first approximation, it's actually proportional. The more HAPs we have, the more NOM is removed. Now, having said that, we spent a lot of time trying to figure out if it's not the gel that's forming, that's causing the fouling here, what is? And I'm just going to give you one snippet of what we found out. Again, this is sort of more chemical fundamental stuff, and be able to talk to anybody who's interested about it later. So this is size exclusion chromatography output showing the molecular size of molecules in various solutions, organic molecules. And the way this works is that the big molecules come out first, and then as we go along here, smaller and smaller molecules come out of the column. So this is a way to take a mixture and identify how big the molecules are. Okay? And so this is the feed, and we see that there's some big molecules here, and they come out in sort of chunks of different molecular size. But there's several peaks that represent different groups of molecules of different size. And this is the feed water from Lake Pleasant. And when we did a test where we just did the adsorption, we took the feed water and we mixed in HAPs. This is not with the membrane or anything, it's just mixing the whole thing up. We got this blue line, and the blue line shows that the HAPs, when they collect organic matter in the bulk, remove some of the biggest molecules and a bunch of these medium-sized molecules and almost none of the small molecules. Okay? That's if it's all mixed together. Then we did the same thing with the permeate from a system where we put the HAPs on the membrane. Okay? And what we got was this. Still, the HAPs don't remove those small molecules, and they barely do better at removing these sort of large or smallish intermediate sized molecules than the straight mixing in the solution. But what they do much better than the adsorptions in the bulk experiment is they remove stuff from this peak and from this peak. So the largest molecules are being removed better by what we're calling micro-GAF, I won't even go through it. The system with the predeposited HAPs layer is, for some reason, removing groups of molecules that do not get removed when the particles are widely distributed. Right? And we think that's probably because these molecules either form that gel layer or they are responsible for fouling in other ways. We don't have a complete explanation, but at least we found something that's different about the two kinds of contacting modes. Okay, now that was great, but there's one big problem here. Remember I said that membranes have to be backwashed. Well, using HAPs doesn't eliminate that requirement. Right? We still need to backwash the membranes. We still expect that ultimately the pressure is going to build up and we're going to have to wash the particles off and put new particles on. So no matter how well it works in the first test, which is, I've only shown you single tests, we've got to get those particles off effectively and be able to put new ones on, or the process will never work for more than a day. Right? So first of all, we took those membranes that I showed you, the little circular ones, and we just squirted them with a squirt bottle to see what would happen. And again, I'm not talking to you today about the use of activated carbon in deposited layers, but we did look at that also. This is the clean membrane before it's ever used. This is the fouled membrane if we don't have any adsorbent on it. And you can see, again, it's like I showed earlier, the gel layer covers the surface. Right? This is what happens when we put a predeposited layer of HAPs on, run an experiment, get those HAPs plugged up with organic matter, and then squirt the surface to rinse off the HAPs. You tell me if that's any different. Okay? This is what happened when we did the same thing with powdered activated carbon. It looked to us like the vast majority of the powdered activated carbon came off the surface, but some of it got stuck. And so what we concluded was that, again, we got lucky. We got very lucky. Because what's happening here is that although the upper layers, the layers closer to the feed solution of the powder activated carbon, do get flushed off, a lot of the carbon that is right next to the membrane gets stuck to the membrane, and we think that's because the NOM is gluing it. It's forming a gel there and it's gluing it. But for whatever reason, those molecules that form the glue seem to stick to the top of the HAPs layer, so they don't cause the HAPs near the membrane to get stuck. Okay? So that was good news, but again, this is just one experiment where we rinsed. Now we wanted to see what would happen if we really did some backwashing. So here I have a second summary of the results to date. Natural organic matter coagulates on HAPs at the top of a predeposited layer. Increasing the HAPs layer thickness increases the NOM removal efficiency and the fouling mitigation. The key foulants appear to be high molecular weight materials. They also, we found, are not molecules that absorb UV light, and they're molecules that don't fluoresce. That's interesting to chemists. And a layer of exhausted HAPs can be easily removed from a membrane surface. Oops. But so far we've only shown that that surface can be cleaned once. What about if we have to clean it many times over long periods? Okay. And so we did an experiment where we did multiple backwashing, but you couldn't do multiple backwashing on a little flimsy piece of membrane. We had to go to a different physical setup. Okay? So I'm going to show a cartoon now about what we did, and then I'll show you the results. And the cartoon makes it look like this is the cartridge stuff, but it's not really. I'll explain in a minute. So the first experiment we did was just what we talked about before. We took water from the lake. We mixed it for 30 minutes with the HAPs or with alum. Then we let it settle for 2 hours. We took the particles out, and we took the supernatant from the settling, and we applied it to a membrane. And we ran that for 2 hours and determined how the membrane performed, how much fouling there was. And then, after 2 hours, we backwashed the membrane that took 2 minutes. So we pushed water up through the downstream side, pushed it up. That knocked off the particles and the NOM. We took that away, and then we went back here and we fed it again. So we did that over and over on a 2-hour cycle. Okay? And then we also did something like that with our predeposition process, but in this case, again, we didn't add the HAPs to the raw water. We put the HAPs on the membrane, and in this case, we used an amount of HAPs that would be used in 11 of these cycles. All right? Therefore, in order to treat the same amount of water with the same amount of HAPs, we ran this for 22 hours. We did that because, as you can guess, we wanted to leave ourselves a couple hours to investigate things and work on a 24-hour cycle. Okay? And then, after 22 hours, we backwashed this membrane and we knocked these particles off. And we wanted to compare these processes, and we could do this multiple times. And the reason we could do it multiple times is that here's what we did. We took not a flat sheet membrane, but a tubular membrane. And we first deposited HAPs on there by taking our stock solution of HAPs, passing it through and recirculating it here. But while we were recirculating it, we were permeating water through the walls of the membrane, which caused the particles to migrate to the walls and stick on the walls. Okay? We did that. Then we switched to the lake water. We passed the lake water through this tube under pressure. Now we closed off the downstream end, so it was dead-end filtration. The water came in here, and it had only one place to go, which was out through the walls of the membrane. But in order to get to the membrane, it had to pass through the HAPs. Okay? And here's the membrane we used. It's a ceramic membrane. It actually is not used commercially for large installations. This is something that's used for backpackers to drink through when they're using, when they're out in the backcountry and are using water of uncertain quality. And so it is a commercial product, but it's not used for large-scale installations. But we used it because the people who make it are partners in the research. Okay, so here's the result. Here's the control experiment. we used that membrane, that tubular membrane, and we passed water through, and we just looked at how the pressure built up over time as a function of the time of treatment. And here, okay, so that's the control. And now we're backwashing this every 2 hours, but you see the pressure is still building up, and that says that backwashing isn't being very efficient. We're knocking off some of the contaminant, but obviously some of the stuff is staying behind every time, so that on the next cycle, it takes more pressure to push water through than it did on the previous cycle. Okay? Then we did this with alum added to the water, and we backwashed every 2 hours, and it improved matters a lot. This is much more like what goes on at a real treatment plant. You mix the alum in with the feed, you filter it, and for several days, you can get good performance with very little pressure buildup. Over time, the pressure does build up because, once again, there is some fouling that cannot be reversed by hydraulic shear. But you're doing a good job. And again, this is being backwashed every 2 hours, and backwashing only takes a couple of minutes, so it's not a big deal. We did the same thing with HAPs, and we got almost the same result. You know, I wouldn't argue that this is better, but I mean, it's at least comparable. So HAPs are performing just as well in terms of pressure buildup, but there's still some of them being left behind, or some foulant is being left behind, and that's what's happening. What about when we did the 22-hour test? Well, there we have it. The 22-hour test. Now, this is, I believe this is about 4 days, as I recall. So every 2 hours, that means 12 times a day for 4 days. So these are about 50 backwashes each. This is 3 backwashes, 1 day, 2 days, 3 days. When we backwash this system, essentially all the fouling material must have gotten washed out because there was almost no buildup over time. Now, obviously, we could have gone on longer, but we felt we had proved our point that, once again, we can backwash and clean the membrane very effectively and better than is done in the conventional process. And this is what the backwash looked like. This is the fresh HAPs. This is what the backwash looked like when we used our pre-deposited system. The material comes off as chunks, and what you can see here, interestingly, is those little things that look white. That's where a chunk is broken, and you see the inside of the layer, because remember, the inside of the layer is white, the outside of the layer is brown. Okay, now what about NOM removal? Because remember, we want to do 2 things, not just reduce fouling, but also remove NOM so that we don't form as much disinfection byproduct. Here's the membrane by itself. It removed about 10% of the NOM. Here's the alum-treated system. It removed about 40%. Here's the HAPs in the conventional dosing mode. It removed 50 to 60%. And here's the HAPs in the pre-deposited mode. And you can see at the beginning of a 24-hour cycle, it removed 80% of the NOM. And then it did gradually deteriorate, but even at the end of a 24-hour, 22-hour cycle, it was removing more NOM than any of those others. So we felt like we had hit the jackpot. We were reducing fouling and doing a better job of removing NOM. There didn't seem to be a lot of downside. You know, there are some, which I'll tell you about in a few minutes. Okay? So now we ask ourselves, what do the HAPs do, and what does the membrane do in these systems? Well, the HAPs layer is responsible for NOM removal and fouling mitigation. That's what we want to achieve, and that's what we're doing. The membrane holds the HAPs there, and it removes very small particles like viruses, which are too small to be removed by HAPs. Right? Might it be worthwhile to have separate units that are optimized for these 2 different processes? And so here's what we did. We went to a 2-step system where, rather than having the membrane be the thing that both holds the HAPs and is the membrane, achieves the membrane results, we took a mesh. This is a nylon mesh. It has 5 micron openings. This is a sheet of it, what it looks like. This is a high magnification picture of it. We took this sheet, we rolled it up, we put it on a backing, and we basically made a tube that has the mesh as its surface rather than the membrane. And the reason we did that is that this 5 micron opening we thought would be better for allowing water to pass through than this membrane, which had 0.2 micron membranes. All right. So here's, again, the cartoon for what we did. We first put the HAPs on the interior of the mesh tube. Then we passed water through the mesh tube, which forced the water to pass through the HAPs, and we took that treated water and put it through the ceramic membrane. Okay? And here's the result. For the mesh tube, we measured the pressure difference across each tube. And for the mesh tube, we did this on about a 12-hour cycle. Notice these pressures are very low. This is peaking at about 30 kPa or about 4 to 5 psi. It's a very low pressure. And each day the pressure built up, and then we were able to backwash it. But the neat thing here is that we showed that we could backwash it for more than a week. And after ever backwashing, this mesh was essentially identical to when it was clean, when it was new. The pressure went down to effectively 0 and built up following more or less the same pattern day to day. Right? Then as part of the same test, we measured the pressure loss across this column. And let me emphasize that we backwashed this column every 12 hours, but we ran this column for 8 days without ever backwashing it. We just fed the water directly to it, never cleaned it. This is the result. This is the pressure across the membrane. It never built up at all, 8.5 days. I have a Polish postdoc working on this whose English is almost perfect. But she came to me one day and she said, "This is blow-minding." So she's working on that. I love that line. But it is blow-minding, don't you agree? We went for 9 days using a membrane to treat water that normally has to be cleaned every 1 hour or less. And we never had to do it. We have no idea how long we could have kept going. It's remarkable. All right, here's the NOM removal in that test. Again, 70 to 80% at the beginning, 50 to 60% at the end. Very consistent. Things looked great. And finally, we went and did the test that's getting closer to reality, which is this. This is the tube that we were using, and we used this upstream tube. This is fine. But remember, we're using the ceramic tube downstream, which is not a commercially viable kind of unit for large-scale installations. Because remember, way back at the beginning, I told you that you have to use this because the flow rate is so slow through each fiber. You couldn't do this with tubes that are this big. You'd have a footprint that was way too large to be affordable. So we ran the test again, still using this membrane to hold the HAPs, or not this membrane, this mesh to hold the HAPs, and this stuff downstream. Of course, we had a smaller version of it. And this always takes a while to come up because there's so many data points, but it will come up in a second. There we are. Here's the mesh. We were operating this now at a higher flux, and so the pressures were a little bit higher so that we could push more water through every day. But again, operating pretty consistently, one run to the next. And here's the real commercial ultrafiltration unit over the course of, in this case, 5.5 days, going from 18 kPa up to about 30 kPa, or 2.5 kPa per day. Remember, 100 kPa is an atmosphere. So basically, we could go 40 days, if this continued, 40 days before the pressure built up to 1 atmosphere. And once again, this was never clean during the whole time. We showed this. I'll tell you one last anecdote, and then we'll finish up. When I showed this to the project officer, this work was funded by Office of Naval Research. You had to know this guy, so I'm not sure this is going to come across all right. But he said, now wait a minute. Are you telling me that you passed water at 100 LMH, which is higher than is normally used for this kind of membrane, commercially, for 5 days without backwashing it? And that's what you got? I said, yes. He said, for 5 days? Yeah. Without backwashing? Yes. 5 days without backwashing? Bill, enough already. You know? So anyway, all right, couple of last slides, just other things that are interesting about this, this process. Here we have DBP data. This is the formation, just look at this last column, formation of trihalomethanes, which are the carcinogens, one of the highly regulated materials in drinking water. If we chlorinate the feed, we got 237 micrograms per liter of them. If we used the pre-adsorption, that's just mixing the HAPs in with the water, we got from 90 to 125. So it was about, it was good removal. These are for doses of 20 to 100 milligrams per liter. But for predeposition, we got better removal of DBP precursors than with predeposition. This is what we expect alum would be. Alum behaves very much like preadsorption, but we get better DBP removal in addition to better, all the other advantages. When we took the sludge from the backwash, so remember that flask with all the brown stuff in it, and we just tried to pass it through or use a mesh to concentrate it, we got a little muffin like this. Right? And this is when we heated it, but this is what's important. Here's that stuff. We did that. We formed this little muffin using a maximum pressure of 7 psi, or half an atmosphere. Okay? When you take alum sludge, remember what that alum sludge is. It's water balloons. When you take the alum sludge and you try to compress it, you've got to apply dozens or hundreds of psi in order to squeeze that water out, because the water is tied up with the sludge particles. Here, the water's already been kicked out, and so we can, we believe, reduce the sludge processing costs in addition to everything else, and thereby make it easier to transport the sludge to a landfill. And finally, I always get this question, can you regenerate the particles? The answer is yes. This is the used particles. This is what we get when we regenerate. We have regenerated using a mixture of hydrogen peroxide and heat. The black dots here are data for removal of NOM as a function of dose for the brand new HAPs, and all these other curves are for various regeneration schemes. And the bottom line is that when we regenerate, the particles are just as good at adsorbing organic matter as when they're fresh. The problem is that this is probably, the way we're doing it now is not economical, so I don't want to claim that we're ready to commercialize this. All right, so after 20 years, is the Holy Grail within reach? HAPs can be pre-deposited on a porous support, which can be operated with 1 to 2 backwashing steps per day, removing 50 to 80% of the NOM and reducing the DBP formation potential. Downstream membranes can be operated at higher than normal fluxes with no backwashing for weeks or longer. The process appears to work with multiple types of membranes and a wide range of feed water qualities. That's work that I didn't show. The scale-up and the economics remain challenges, and most importantly, this is the most fun I've had in 20 years of research. So I didn't leave a lot of time for questions. I apologize for that, but I'll be happy to answer a few, and then I'm here for the day. So. These are the students and others.
Questions for Mark?
So Mark, I'm just curious if there are other materials that will work. Because I think about when we clean up samples to run before LCs to remove organic matter and stuff, we use silica or alumina particles, which are small little things too, and those are widely and commercially available. Would they work as well?
We have tried silica, and it sticks the same way that PAC does. We have not tried commercial aluminum hydroxides. I don't know how to answer that. We've also tried iron hydroxide heated in the same way, and iron hydroxide behaves just about like the aluminum does, although the aluminum is a little bit better, so that's what we stuck with. But yes, there are undoubtedly other particles that work better. One of the interesting things that we're doing now, which I think might be the best way, is that we're dosing little bits of PAC in with the HAPs. So the PAC is not, the whole layer, but still the PAC does collect some material that the HAPs don't. So we get the benefits of both of them attracting the things that they are best at, but the HAPs are the bulk, so that the other advantages of the process seem to be working. Yeah. Oh, okay.
So your HAPs remove 70 to 80%. So 20% are getting through to the second tube with your membrane. So I can understand if it fouled 4 times slower or a third slower, why is it not doing that?
Well, it's not doing that because NOM is a mixture of a gazillion different kinds of molecules. And again, we seem to be lucky, but lucky partly in the same way that people have been always. Alum and ferrochloride, the conventional coagulants, and our particles do selectively remove certain fractions of the NOM. You saw it, they remove the larger molecules, and there are other characteristics. It happens that it's removing the things that cause fouling more than the things that don't cause fouling. So the 20 or 30 or 40% that breaks through is passing through the membrane, is not causing a problem. Other than that general result, I don't know why, but that's what's happening. Right?
So it seems kind of counterintuitive that I think you mentioned, although you didn't show the data, that the large molecules that were fouling also were low UV absorbing. Did I catch that correctly?
No. I mean, that's a reasonable interpretation, but I didn't mean to say that exactly. The HAPs selectively remove the high UV absorbing material. In fact, the SUVA of the material that gets removed is as high as 20. I mean, it very strongly removes things that absorb UV. But we have found other materials that absorb UV light, or that absorb the NOM that has high UV absorbance, and that those particles don't reduce fouling. So you got this UV absorbing NOM, and it is very selectively removed by HAPs and by other things. But you have other molecules that are causing fouling, and those are selectively removed by HAPs, but not by other particles. So in other words, we have 2 different particles, both of which do a good job of removing UV absorbance, but HAPs also reduces fouling and those other materials don't. And since those other materials remove UV absorbance without reducing fouling, we conclude that the UV absorbing materials are not the foulants.
So are they polysaccharides? Is that what you're suggesting?
That's the most likely candidate, yeah.
We have time for one more question.
It's a follow-up for the previous questions. It's about the two-step system, and you said that some particles or natural organic matters are removed by the pretreatment, the HAPs, and some others are removed by the membrane. But the ones removed by the HAPs tend to contribute to the fouling. What do you think the factors be that contribute to the fouling? Could it be the surface charge, or could it be, so what kind of particles are they?
As Ray suggested, we think the most likely group of molecules to cause the fouling are polysaccharides because they fit all these characteristics. They don't absorb UV light, they don't fluoresce, they are relatively high molecular weight, which means they are being removed by the HAPs, according to our SEC analyses. And we have used surrogate polysaccharides, particularly alginate, and we have found that HAPs, in fact, does collect alginate. So that's an indicator that, that the HAPs are removing that material. So we have lots of pieces of evidence that point towards polysaccharides as the most likely group of contaminants that cause fouling. But they're a tiny, and they are a tiny fraction of the total NOM, so it makes sense that they don't necessarily follow the same removal efficiency patterns. If we just measure gross NOM, it doesn't tell you anything about the polysaccharides. Some adsorbents remove most of the NOM, but don't remove polysaccharides, and those adsorbents don't reduce fouling. Our adsorbent happens to remove both, and we were, like I say, we're lucky. But I think that's the most likely group. Thank you.
Thank you.